Alright guys, welcome back. In this video I just want to introduce the three-moment equation and talk about how we can use it to solve for statically indeterminate beams to get the reactions in the shear force diagram and bending moment diagram. So over here we have the three-moment equation. There's more than one way to write it, but this is the way that I like to write it. It makes sense to me. Basically what it is it compares three moments across two spans of a beam. So if this is span 1 and this is span 2, and then we're going to have 3 points. We're going to have point A, which is on the left of span 1, point B, which is on the right of span 1 and the left of span 2, or basically the point right in between, and C, the point on the far right-hand side of span 2. Now, some people write this a little bit differently. Some people write L, C, and R for like left, center, right. Some people, when they're talking about using subscripts 1 and 2, like I would have L1, this would be the length of section 1. Some people might refer to that even as like LAB or something. So just depending on, just watch out for the subscripts when you're looking at this, and depending on who's written the equation, it might look slightly different depending on what that person prefers. The other thing to notice in here is if you have a constant EI the whole way across, then this EI is going to drop out the whole way. If EI is like double on one side or something, then just pay attention to that and make sure to include a 2 at the bottom basically. But otherwise EI, flexural rigidity, is in every denominator, and so usually that drops out in these equations as well. Alright, so what we want to do basically is we want to be able to draw the bending moment diagram for a problem like this. But what we can do is, instead of just drawing the entire bending moment diagram right away, we can use the principle of superposition to kind of draw it a little bit by parts. So the first part, when we're doing it by superposition, would be to just draw each span as if it was simply supported that's carrying the applied loads. So those would look like this, where for a simply supported beam with a point load right in the middle, we'd get this triangular shape that's a height of PL/4. And then for a simply supported beam with a distributed load, we'd get this parabolic shape with a height of WL²/8. Now you can find these values in tables, or you can just do it with a virtual cut and a free body diagram, and you'll figure out that these are the heights there of these bending moment diagrams for the simply supported situations. Now, when we do draw these as simply supported, you'll notice that the ends of simply supported beams, the moments are always 0. Now that's cool when we compare it to the actual structure, because MA, the internal moment at A, will actually be 0, and the internal moment at C will be 0 because they are at the ends of spans that aren't subjected to an applied load or at a rigid connection or something like that. And that's going to be helpful for us when we use the three-moment equation, because you'll notice there is MA, MB, and MC in here. Well, in a problem like this, we know that MA and MC are going to be 0, and so really that's going to simplify this a lot. But they might not always be 0. For example, if you have an overhanging beam, something like this, maybe with a point load at the end, MA would no longer be 0. But really, MA would be really easy to find, because you could just take a virtual cut there and the magnitude of this point load times the distance, and you'd be able to find MA. But so MA, typically the edge moments like MA and MC will be known or pretty easy to find just by using statics before you actually proceed with the rest of the problem. So anyways, moving on with the principle of superposition. So we start out with the bending moment diagrams as if they were simply supported and just carrying the moments basically caused by the applied loads. So then what we want to add in is the moments just caused by the supports, because we need to include the end moments here if they are existing, because the actual moments on the actual bending moment diagram are maybe not 0 at all of these points. And so to account for any non-zero moments at A or C, we draw them on like this. But in this case, we'll get to it in a second, but we do know that MA and MC are going to be 0 anyways. And then we also draw the internal moment at point B here due to the reaction at B. Okay, so we have the internal moments caused by the applied loads and the internal moments at the supports. And if we were to add those together using the principle of superposition, we would end up getting something that looks like this for this problem. Now, MA and MC in this problem are 0, so basically the superposition of this graph and this graph, well, it's just basically this graph, because this one is just a horizontal line that equals 0, because it would be 0 here and 0 there. So basically we have this triangle and this parabola coming from right here, and then we have this long triangle like that goes the whole way along the bottom. Now, if you add these two together, basically what we can even do is, I like to put a little bar on this side and label this as the bending moment diagram. So this is like the actual bending moment diagram if we just add this line at the top to this line at the bottom, basically at every point going along the span. And if we did that, it's going to look something like this, where this would be the actual bending moment diagram for this system. And you can look at this like where we're adding 0 plus this negative value, we're getting this negative value down here. At this peak right here, we have this positive value plus this negative value nets out to this positive value. And then somewhere in here, like if we add the peak of the parabola plus half of this triangle, the height here, we're getting the height of the parabola at midspan here. Now the interesting thing to note that is this is a good way to do these problems graphically if you're dealing with point loads, because adding triangles to other triangles and straight lines, it's really easy to do graphically, and you can generate the bending moment diagram pretty rapidly. But in these regions where we're adding parabolas to straight lines or to triangles, it gets a lot messier, and this problem becomes actually a little bit trickier, and this sort of becomes not the best way to solve the problem, but it is possible. But you'll just notice like it's complicated because the actual maximum of this parabolic shape is not going to be at the mid-span of this section. It's going to be over to the right a little bit, and it's just kind of a headache. I'll do an example, I think, where we actually solve it this way, but and I'll compare it to an example of solving it the other way, just so you know. But this is one way to basically get the bending moment diagram, is to fully like graphically do this with addition. The other way that we can go about this is if we come back up to the three-moment equation, we basically just plug and chug the whole way along. The only things in here that we don't know yet is this A1. A1 is just the area. This is A1. This is the area of the simply supported bending moment diagram that's carrying the point loads. And then this is A2, the simply supported area, the area of the bending moment diagram of the simply supported diagram that's carrying the loads in this section. And then x bar 1, basically the centroid of this shape, is the distance from that centroid to basically the left-hand side. So this would be x bar 1, and then the distance from this centroid over to the right-hand side, basically just going to the outsides that we're looking at for the two-span section. This is going to be x bar 2. So basically, you find this area, you find the distance of the centroid. If it's not, if this shape is not symmetrical side to side, then you might have to do a little bit of composite areas or something to find the location of that centroid. But basically, you just plug and chug in here. In this example, we know that MA is 0, MC is 0. So the only real unknown in this whole problem, this whole expression, would be MB. You would calculate for MB, and then basically you would get, once you know MB, you would know the internal moments at A, B, and C. And if you've watched the slope deflection method problems, then from here on it becomes exactly the same method. So once you determine MA, MB, and MC, then what we do is we draw each span with a virtual cut just before each support. And once we label on MA, MB, and MC, which is the actual moments right at those cuts, then we can label on VA, the shear at A, the shear on the left-hand side of B, the shear on the right-hand side of B, and then the shear at C. And another thing you have to do also is you draw on the applied loads. And now you can just use these as free body diagrams to just solve for the shears at each end, because you can just do sum of moments about 1 point, and then do the sum of vertical forces. And then from there, you'll know the shear and the moment just on the end of each span, just to the side of each of those reactions. And then from there, you can use that to plot the shear force diagram and then the bending moment diagram. And then off the shear force diagram, you can calculate, or you can just pretty much pick off what the reactions are. So this method seems to be a lot more straightforward and usually easier and less prone to error than trying to graphically draw the bending moment diagram by summing up the two functions. But like I said, I'm going to show some examples of both. But yeah, that's kind of the general method about how the three-moment equation works. It's kind of weird to talk about it without doing an example because it's a little bit abstract. But join me in the next video, and we'll go through an example with actual numbers, and you'll see that it's actually not so bad.